Okay, next lesson about oxidation number, second one. So last lesson we said, what is oxidation number? New concept, bit of a dodgy concept in some ways, but very useful. How many electrons is something short of? Okay, I think we use water. Okay, and we can see there that there's not, although it's covalent, there's not even sharing of those electrons, because oxygen is a lot more electronegative. So if you like, hydrogen is kind of missing out on one electron there, so it's +1 oxidation number, same with that one. And the oxygen is gaining 2 electrons it shouldn't really have, so that's a -2. And if we check that the sum of the oxidation numbers equals to the charge on the species, which is 0 for water, so that's what we did last time. Right. Now, oxygen is always -2, and hydrogen always +1. There are actually a couple of exceptions to that, and well, then I'm going to talk about three exceptions to that rule. I think. Let's talk about oxygen first. Right. Now, which element is more electronegative than oxygen? Of course, it is fluorine. Yeah, fluorine is more electronegative. So let's think about a compound of oxygen and fluorine. Let's change that. I'm going to swap those hydrogens for 2 fluorines, OF2. Now, oxygen will not have an oxidation number of -2 in this, because who's getting more than its fair share of electrons in this bond? Well, it's fluorine. So fluorine is going to be -1. It's getting more of that electron than it should have. And this one's going to be -1. Add all the oxidation numbers up, it's got to add to the charge, which is 0. So that means oxygen there has actually got an oxidation number of +2. So this rule, oxygen is always -2. Not quite true, because when it's in fluorine, it's going to be +2. So we'll add all these ones on afterwards. So we'll say except in fluorine compounds, and that reminds me, fluorine is always going to be oxidation number of -1, always, because it's the most electronegative element. Let's think about another one now, hydrogen peroxide. This is another exception because, hydrogen peroxide, right, is H2O2. Now, what's the bonding like in that? Well, we know oxygen has always got to form 2 bonds, so it's actually like this. You get a single bond between the oxygens, that's called the peroxide group, and you get a hydrogen attached to that one and a hydrogen attached to that one. Right, let's think about the electrons in that bond. Well, hydrogen is getting more than is losing out there. So oxygen's getting most of that electron, so it's +1 for that. And this one's going to be +1, of course, as well. Now let's think about this oxygen here. Right, it's not going to be -2 oxidation number, because the black electrons there, yes, it is getting more than its fair share of them. But look at the oxygen here. It's sharing them with oxygen. It's got the same electronegativity as the other oxygen, so it's only getting its genuine fair share of those electrons. So the oxidation number of oxygen there is -1, and this one is -1, of course. And if you add them all up, well, the charge on the species is 0, isn't it? And they all add up to 0. So that's another little exception there. So put that in there. Except in H2O2 when it is -1. Right, now let's talk about this. So that is hydrogen peroxide, actually is a pretty common chemical, and come across it all the time in A-level chemistry. So that is important to remember. Oxygen is -1 oxidation number there, it's not -2. The one with fluorine, don't really come across that very much, so you kind of don't worry about that too much. Right, the third exception to the rule, I said there was 3, and that's not with oxygen, that is with hydrogen. Okay, so hydrogen is nearly always +1, but sometimes, not very often, hydrogen forms a hydride ion. And the hydride ion is H-, so it's pretty rare. You may think, well, why is that quite rare? Why is, because hydrogen's got 1 electron, it's outer shell, isn't it? So surely with the hydride ion, it's going to have 2 electrons, yeah? It's going to have a full outer shell, so it's going to be pretty stable. Well, it doesn't form very often, because if you think about it, you are sticking a whole extra electron onto a tiny little hydrogen. So the charge, that there's not, that extra charge hasn't got much space to spread out. So, okay, it's very high charge density. Whereas if you think something like chloride ion, that's massive, isn't it? Okay, that's got an extra electron, but you've got one electron and it's spread over a much larger volume. So that's, chloride ion is pretty stable. Hydride ion we don't come across very much, but when you do, obviously the oxidation number of hydrogen in the hydride ion, it's got one electron it shouldn't have. It's not short of any. So here it is an oxidation number of -1. So that's the other exception there. It's -1 in the hydride ion. Right, so that is that. There aren't any other exceptions that I can think of anyway. That's it. That's it for oxidation numbers. That blue box with the little red annotations in there. That's all you need to know. Let's just do a couple more assigning oxidation numbers, maybe slightly trickier examples than we did in the last one. Okay, so in organic chemistry, you've come across, probably by now, you've come across potassium dichromate as an oxidizing agent. Right, and the formula of that is K2Cr2O7. So let's find out the oxidation number of chromium in that compound, okay? Right, so the first thing we're going to do is, those potassiums, they're always +1, aren't they? Potassium doesn't form anything except the K+ ion. No other species, okay? So that means that the charge on the dichromate ion is Cr2O7 2 minus. So let's work out the oxidation number there. Charge in this, so sigma oxidation number is equal to the charge. So, right, the charge in the species is -2. There are 2 chromiums, they're unknown, so put 2 Cr there. And we have got, right, each oxygen, we've got 7 of them. Each one's -2, so that is going to be -14. So 2 Cr is equal to +12. So chromium has got an oxidation number of +6. That's a pretty high oxidation number, and that makes chromium a pretty good oxidizing agent. And that's why it can oxidize alcohols. Okay, let's have a look at another one. This will be a very unfamiliar compound. It's called ammonium metavanadate. Okay, and vanadium is a transition metal, V. The formula of the compound is NH4VO3. Now, what we're going to do there, well, you do need to have a bit of appreciation of chemistry there. As well, NH4, that is quite obviously the ammonium ion, NH4 plus, isn't it? So that means this bit here, it's an ionic compound. This is going to be the VO3 minus ion. Right, let's work out the oxidation number of that. So the charge on the species is -1. Vanadium, we don't know. Oxygen has got an oxidation number of -2, so that's -6. So that means vanadium is equal to +5. Vanadium has got an oxidation number of +5 in that compound. So that was a little bit tricky. Okay. I'll give you another weird one. Okay, so here's this compound here is not sodium thiosulfate, which is S2S, which is that. Okay, it's not that. It's S4O6, that compound. So let's now work out the oxidation number of sulfur in that. Right, now we know sodium is always +1. It's like potassium is in group 1 metals. They only ever form +1 ions. So that means we've got this negatively charged ion here. It must be S4O6 2-. So let's work out the oxidation number of sulfur there. So the charge on the species is -2. The sulfur was 4 of them. And we've got 6 oxygens, each one's -2, so that's -12. So 4S is equal to +10. So that means S is equal to 2.5. And that's where you think, oh, I've gone wrong, because it's fractional. And we've said oxidation number. What is oxidation number? It's how many electrons are missing, or how many it's short of electron. Okay, obviously you can't break an electron into 2, so what's gone on there? Well, you probably won't be that surprised if you think about it. To think what actually happened here is you've got this thing S4O6 2-, and the sulfurs aren't actually equivalent to each other. What you've got is you've got 2 of them with an oxidation number of +2, and you've got 2 with an oxidation number of +3, so that's kind of an average value of the 2 of them. Okay, so that is pretty rare you get fractional oxidation numbers, but you do sometimes, and it's usually because, it's always because those sulfurs are not in equivalent positions. Okay, so now leave that there. In the next video, we're going to talk about what can we use oxidation numbers for. Hopefully we can assign them. Now we're going to see what can we actually do with them.